Today we are going to create a function that performs the composite Simpson's 1/3 rule in MATLAB. And so what I have here is just a quick recap on the formulas that were derived in the previous two videos. And so this right here is Simpson's 1/3 rule. Okay? And I have actually an equal sign here. This should say approximately. Okay? All right, it's approximately equal to this integral. You can see that we have a couple sums in here. So we will need a for loop so that we can compute these two sums here. Okay? And just like with trapezoid rule, there will be two terms outside of the for loop. Okay, right? We'll just compute these separately. Okay. But after we add all those together, we'll multiply by b minus a over 3n. Okay. And there is something else we need to be thinking about before we start coding this in here. One of the things is we needed a even number of subintervals, and we need at least, so I wrote greater than 3, but I should actually say 3 or greater. Let me fix that. Okay. So if we have less than 3 points, then we don't have enough points to perform quadratic interpolation, right? That's the whole idea behind Simpson's rule, is connecting every three consecutive points with a quadratic polynomial. Okay, so we can't do that if there's less than 2. Okay, and if we have an odd number of subintervals, then things won't work out quite right. Let me show you what I mean by that. Okay. Well, if we say had an odd number of subintervals, so here we have 1, 2, 3 subintervals. Well, we would be able to perform that quadratic interpolation on the first 3 points. Okay. But then the question is, well, what are we going to do over here? Okay. There's only one other point to connect to. Okay. We need an extra point or an extra subinterval to ensure that we have another quadratic here. So that's why we always need that even number. And there's one other piece of information we need before we start coding. And there's actually more than one way we can address this issue, but the issue I'm trying to address is this even number of subintervals. So what's one way that we can tell whether a number is even or odd? And one way is we can use modular arithmetic. But before we get into the even and odd part, let's just kind of get an idea of what modular arithmetic is. Okay. And so you've actually done this plenty of times here. So let's say we had 15 mod 12. What does this mean? Okay. Well, this means that we want to take 12, divide it by 15, and then find the remainder. So this remainder is our answer. It's 3. Okay. And you actually do this all the time, right? 3 p.m. Well, that's equivalent to the 15th hour of the day. Right. Let's try another one out. Let's think about even and odd here now. Let's maybe try 7. Yeah, we'll do 7 mod 2. Okay. So mod 2. This is what we want to be using is mod 2 when we're thinking about even and odd, and we're going to see why. So if we take an odd number like this, the question is, well, what's going to happen? Well, of course, we're going to end up with a remainder of 1, and let's actually see it. So 2 goes into 7 3 times with a remainder of 1. Okay? And that should happen for all odd numbers. That remainder should always be 1 if we're working in mod 2. And lastly, if we were to try out an even in mod 2, so 2 goes into 8 4 times with a remainder of 0. So this would just be 0. Okay. And the reason I wrote MATLAB over here on the side is the way that we would type this in would be mod 15, 12, and MATLAB would spit out 3. And if we were to try mod of 7, 2, MATLAB would spit out 1. And of course, mod of 8, 2, MATLAB will give us 0. All right, let's go ahead and jump into MATLAB and start coding. So as what we have here is I have copy and pasted the trapezoid rule function that we created yesterday from basically the for loop and up. Okay. And all I've done so far is I've changed the name of the function to simp13, and I just adjusted that here in the comments. And that was the only thing I had to adjust. Okay. Composite Simpson's rule. Okay. Let's real quickly run through this stuff here again. So the top here, if there are less than 3 arguments, whether we're using Simpson's rule or trapezoid rule, that's going to be a problem. We need at least the function and the limits of integration. Okay. However, we can leave out n, because if you do leave out n, we're going to use a default of 100. Okay. And there was one more little thing we had added in here. If b is not bigger than a, right, this little tilde here, when we're talking about logic, is going to mean not. So if b is not greater than a, we're going to have an error here. We want the lower bound to actually be lower than the upper bound. Okay. Moving down, okay, you might remember that the very first thing in these brackets here is just evaluating the function. Here we go. I have the right thing highlighted here now. The very first thing is just evaluating the function at a or x naught, however you want to word that, right? A is x naught here. Okay, so f of a or f of x naught. Okay. Let's go see that that is in MATLAB here. So you can see that right before the for loop, we actually evaluate the function at a, which is good. Okay. We also are going to call the first x a, and after that we'll keep adding the spacing to it to get to the next point. Okay. And the spacing we found yesterday also was just b minus a divided by n. Okay, and it's the same here. All right. Now, if we were to look at our sum here, we do certain things when I is odd and certain things when I is even. So let's code that in here. We're going to need some if statements. So how about we say if mod, okay, we're going to take the number I, so I mod 2, okay, and let's see what that first sum looked like. That first sum was for the odds. So if I want odds, I want it to be mod 1. So if, let me start over there. So if I mod 2 is 1, that means that I is odd, right? And that's what we wanted for that first sum. Okay. So let's get that going. We're going to have s is equal to, and right, we want to take our previous s and add our new one to it. Okay, and so let's see what that should look like here again in our sum. It should just be 4 times the function value. Okay. So let's go ahead and go back to MATLAB. Here we are. So 4 times the function value. So func of our new x, okay, and then var argin, just in case we have these extra inputs. Okay. Now, if a number is not odd, it is going to be even. So I'm just going to say else if, then we will perform almost this exact same sum. But let's go back up here and look at what the coefficient is. We have a 2 in front of this sum. Let's go ahead and insert that. So this will be a 2 here instead. And then we can end the if statement, end the for loop, and remember, we still need to evaluate the function at the very last value, so b. Okay, so let's input that here. So lastly, s is equal to s plus func of b, comma, var argin. Okay. And let's make sure we have everything commented out, or not commented out, have everything suppressed. Okay, so let's suppress this calculation of all these x's. We don't want to see every single one of those. Let's suppress each partial sum here. Okay. And in the end, we would like our output, I, the integral, to be what? Let's go back and look at what we have. B minus a divided by 3n times our sum. So b minus a divided by 3n divided by 3 times n, and then this should all get multiplied by our sum here. And that actually ends our function. So let's go ahead and save it, and let's test it out and make sure it's performing properly. And we'll put this up against our integral function. Okay. So let's start off with the Simpson's 1/3 rule. And actually, I just realized there's one more thing that I do want to add to this before we test this out. So remember, we said that we must have an even number of subintervals. So why don't we take care of that here? Why don't we say if mod our number of subintervals, so n mod 2 here, if this number again is odd, that's going to be a problem. So let's say equals 1, report an error. Let's just say n must be even. Okay. That should be perfect. We'll go ahead and end it, and let's give it one more save here. Okay. And actually, I think we can even add in one more thing if we want. Right? We also said that we need to have at least 3 input arguments. So we could also say if n is less than 3, that we would like to also report an error. So n must be 3 or greater. Okay. And end. There we go. Now we have enough flags here built in. Okay. Let's go ahead and save it. And let's pick a function here. How about, we'll keep it simple, x squared plus 1. This Simpson's function doesn't need the dot here, but the integral function will, so I'm just going to put it in. And let's evaluate this integral from 0 to 5. So it says we might be missing some characters. So I'm glad we tested this out. We want to go to line 25. Our else if here should just be an else. Okay. Right? If I have else if, this is supposed to be followed by some condition. So just else, not else if, and that should fix our problem. Okay. This is saying if we get 1 out of this, we'll perform this. And if it's again, if it's not odd, it's going to be even. And so we'll fall into this little formula here. Let's go ahead and hit save, and we'll give this one more go. Okay, so now the question is did this work well? Okay, let's find out. Integral And I'll just actually copy and paste all this right here. There we go. And so we have the same thing. If we did format long, these would differ. But yeah, our Simpson's 1/3 rule seems to be working pretty well. Let's compare it to our trapezoid function. I'm going to go like this. So I'm just going to change this word integral to trap. And keep in mind, we're using the defaults for trap and Simpson's 1/3 rule. So this is performing 100 subintervals. All right, let's go ahead and hit run, or enter. Okay. And so this one differs a little bit. Okay. And this is expected. The Simpson's rule is typically more accurate than the trapezoid rule. Okay. All right, and that is it.